Hey, what's up, Chem Peeps? Mr. Boylan. What in the heck are we going to do in this vid? We are going to perform stoichiometric calculations involving limiting reactants. Oh, things are about to get spicy. As always, breaking it down. Two big things you want to be able to do. 1. Define what the heck an excess and limiting reactant are. 2. Use some stoichiometry to determine the identity of a limiting or excess reactant in a chemical reaction. Oh, I can't wait! Alright, so first thing we need to do, some definitions. Limiting reactant is our first one. This is the reactant that limits the amount of other reactants that can combine and the amount of product that can form. It is the one that's going to get completely used up in a reaction. Second definition, excess reactant. This is a substance that is not used up completely in the reaction. There's going to be some left over. There's going to be some in excess. It's also important to note that you'll sometimes see the words limiting and excess reagents. They mean the same thing. We're just talking about our reactants. All right, now if you're like, whoa, this is too much for me, I think the easiest way to understand excess and limiting reactants is to make some sandwiches. If you take a look at our chemical equation that represents the creation of a sandwich, we need 2 slices of bread, 1 slice of cheese to make 1 sandwich. So what this video is all about is, well, what happens if I start with, say, 4 slices of bread and 1 slice of cheese? I can't make 2 sandwiches, even though I have 4 slices of bread. I am limited to the production of 1 sandwich because I only have 1 slice of cheese. My cheese is limiting how much product I can make. Notice it is completely consumed and there is no cheese left over, but I do have some excess bread. Alright, so now let's talk about how we can solve problems using excess and limiting reactants. There are lots of different ways to do this. I think the greatest way is by using what's called an ICE table. This is a great way to organize what's going on in your chemical reaction and help you understand what's left over and what gets completely used up. Alright, so the I in ICE table stands for the initial number of moles for each species in the reaction. It's important to note that if you're not provided with number of moles, convert using dimensional analysis. You don't want to put grams, you don't want to put number of atoms into your ICE table. Make sure that you're only using moles. And unless otherwise stated, you can assume that the initial number of moles of products is 0. The C in ICE table stands for change in the number of moles for each species in the reaction. It's important to note that the change is determined based on the molar ratio in the balanced chemical equation. The change happens stoichiometrically. Now, as you use ICE tables, you can just randomly choose one of the reactants as the reactant that's limiting. You'll know if you made the wrong choice, and this just becomes easier with practice. And then finally, the E in ICE table represents the end number of moles for each species in the reaction. Important to note that if you end up with a negative amount of moles, perform the ICE table calculation again, but choose a different reactant as limiting. You've chosen the wrong one. Again, this will just make a little more sense with some practice. Lastly, it's important to note that some students find it helpful to call these RICE tables to remember to include the balanced reaction. I prefer ICE tables, but that's just because I'm a Vanilla Ice fan. Alright, let's take a quick look at an example of how we use ICE tables to help us determine which reactant is limiting and which reactant is in excess. Silicon dioxide is usually quite reactive, but reacts readily with hydrogen fluoride according to the following balanced equation. Boom! If 2.0 moles of HF are exposed to 4.5 moles of SiO2, which is the limiting reactant? First, let's set up our ICE table. I'm going to take my reaction and I'm going to write the letters ICE for initial, change, and end, just like you see on your screen. My first step is to set up initial number of moles. Remember that you may assume the initial number of moles of products is 0. So I'm going to write in 2.0 moles for HF, 4.5 moles for SiO2, and 0 moles for each of my products. Step 2. We're going to randomly choose one reactant as the limiting reactant and describe the change in each species in the reaction if that reactant were completely used up. Remember, the change happens based on the stoichiometry. So I'm just going to choose my first reactant in the equation as my limiting reactant. If all of this gets completely used up, it's going to decrease by 2 moles. And if this decreases by 2 moles, if I react 2 moles of HF, I'll use up half a mole of silicon dioxide. Now, why am I subtracting 2 here, but only 0.5 from silicon dioxide? Remember, the change happens stoichiometrically, based on the coefficients in the balanced chemical equation. How does 1 compare to 4? It's a quarter. In other words, whatever amount of HF is reacted, I'll only need a quarter of that amount of SiO2. In this example, if I'm using up 2 moles of HF, I'm only going to need a quarter of that, or 0.5 moles of SiO2. And I'll form 0.5 moles of SiF4. Again, think about the change stoichiometrically. The ratio in the balanced chemical equation between HF and SiF4 is 4 to 1. Whatever amount of HF is consumed, a quarter amount of that SiF4 is produced, plus. And then finally, if I consume 2 moles of HF, I'll produce 1 mole of water. Again, use the coefficients to determine the change. 2 is half of 4. Whatever amount of HF I use, I'm going to produce half that amount of moles of water. Alright, once I've established the change in number of moles of each of my reactants and products, my final step is to determine the n number of moles of each thing in the reaction. Remember, if we end up with a negative number of moles for anything, we've done something wrong. 2 minus 2 is 0. Remember, this is the reactant that I decided was limiting. It was completely used up. So if I have 2 moles of HF and 2 moles is used up, I'm not going to have any left over. If I have 4.5 moles of silicon dioxide and 0.5 moles is used up, 4 moles, 4.0 moles of silicon dioxide is going to remain at the end. It's going to be in excess. And then I will have made 0.5 moles of SiF4 and 1 mole of H2O. So as I look at my ice table, I've identified the limiting reactant as HF. Yes! Alright, that's all fine and dandy, but I'm just starting out. I'm just learning how to do this. What if I had chosen the other reactant? I mean, you said just to randomly choose one. Let's check it out. Let's see what happens if we perform the same ice table calculation, but assume that the SiO2 is the limiting reactant. Again, our first step is to set our initial number of moles. Easy. The change in stoichiometry is our second step. And this time, I'm going to choose SiO2. If that's my limiting reactant, then it will get completely used up. I'll use up all 4.5 moles. As I think about the stoichiometric change, again, it's based on the coefficients. If I use 4.5 moles of SiO2 completely up, that means that I'd have to use 4 times that amount of HF, or 18 moles. Now, some of you will recognize at this point that you've chosen the wrong reactant as limiting, but let me just work it through so you can see. As I determine the change for my other things in the reaction, notice here SiF4 would increase by 4.5 moles if I consumed 4.5 moles of SiO2, again 1 to 1. And my number of moles of water would be 9 moles, because 2 is twice the amount of 1. So final step here, determine the end number of moles by summing together the initial and the change. Here's where we can clearly tell we've chosen the wrong reactant as our limiting reactant. If you end up with a reactant that's negative, or a negative amount of moles, you've chosen the wrong one. We can't actually use up 4.5 moles of SiO2 if we don't have enough HF to completely use it. Oh, math. Alright, that does it for this vid. As always, check out the sample guided practice videos to help you better understand how to use ice tables with excess and limiting reactants. Have a fantastic day.